Have you ever been in a hospital and seen one of those IV bags hanging by a patient's bed? It just looks like a simple bag of water, right? But what if I told you it's not just water? The reason why is this incredible story about balance, biology, and protecting our bodies at the tiniest, most microscopic level.
I mean, think about it. If someone's dehydrated, why wouldn't doctors just pump pure, clean water directly into their veins? It seems like the logical thing to do, right? Well, it turns out doing that would be incredibly dangerous. We're talking potentially fatal. So today, we're going to break down exactly why medical science relies on salt water and not the pure stuff.
So here's how we're going to crack this mystery. First, we're going to cover the basic rules of how water works in our bodies. Then, we'll meet 3 different types of solutions and see the wild effects they have on our cells. We'll find our just right Goldilocks solution, and finally, we'll look at the precise science medicine uses to nail this balancing act every single time.
All right, let's dive right in. First things first, there's one core scientific idea that explains everything else we're about to talk about. It's called osmosis, and believe it or not, it's happening inside you at this very moment.
Okay, check out this diagram. It shows you everything you need to know. On the outside, you have plain old water. But inside that tube, behind that special barrier, you have a really concentrated sugar solution. Now, water has this natural instinct to create balance. It wants to move from an area that's less crowded to an area that's more crowded. And you can see it happening. The water is rushing into the tube to try and dilute that sugar, which makes the water level rise. That right there is osmosis.
So the big takeaway here is actually pretty simple. Osmosis is water on a mission to create balance. It will cross a barrier, like our cell walls, moving from an area with less stuff dissolved in it to an area with more stuff. Just remember that, because it's the absolute key to our whole mystery.
Okay, so we've got the basic rule down. Now, let's put it to the test. Let's see what happens when we take a living cell, like one of our own red blood cells, and drop it into different kinds of solutions. This is where we get into something called tonicity. And trust me, it gets dramatic.
There are 3 main characters in this story. You've got your hypotonic solution, which is less concentrated than our cells. Then there's an isotonic solution, which has the exact same concentration. And finally, a hypertonic solution, which is, you guessed it, more concentrated. Let's see what each one does to our poor little cell. First up, hypotonic. If you put a cell in a hypotonic solution, like pure water, the inside of the cell is way more concentrated than the water on the outside. So, following the rules of osmosis, water rushes into the cell to try and balance things out. The cell swells and swells and swells until, pop, it bursts. Here's a little trick to remember this one. The cell swells up big like a hippo in a hypotonic solution. Hippo, hypo. Got it?
Next, hypertonic. This is the complete opposite. The solution outside the cell is super salty, way more concentrated. So where does the water go? It rushes out of the cell to try and dilute the solution around it. This makes the cell shrivel up and get all wrinkled. For this one, think of someone who's hyper and runs around a lot, getting really skinny. A cell in a hypertonic solution gets skinny.
And finally, our third player, isotonic. This one's the easiest. The prefix iso literally means same. So in an isotonic solution, the concentration outside the cell is exactly the same as it is inside. Water flows in and out at an equal rate, and the cell just stays perfectly happy and healthy. No swelling, no shrinking.
And look, this isn't just a fun science experiment. It has a life or death consequences. This quote really spells it out. That process of cells bursting is called hemolysis. And this is exactly why you can't just inject pure water into someone's bloodstream. It would cause their red blood cells to explode.
So one solution bursts the cell. The other one shrivels it up. If one is too hot and the other is too cold, that leaves us with the one that is just right, our Goldilocks solution.
An isotonic solution is the one that medicine relies on. It perfectly matches the osmotic pressure of our own body fluids. By doing that, it makes sure there's no net movement of water in or out, so our delicate cells don't get damaged. It can deliver medicine or hydration without disrupting that critical cellular balance.
And this is where it all comes back to that IV bag in the hospital. Almost always, it's what's called normal saline, a 0.9% sodium chloride solution. Even dextrose solutions, which deliver sugar, are precisely calibrated to be isotonic, all to keep our cells safe.
So this brings us to the final piece of the puzzle. How in the world do scientists and pharmacists make sure every single medical solution is perfectly, precisely isotonic?
And the stakes here are incredibly high. This isn't just about IV drips. Think about it. Injections, eye drops, nasal sprays, even the stuff they use to wash out a wound. Anything that touches our body's delicate tissues must be isotonic to prevent irritation and damage at the cellular level.
So what's the secret? How do they measure this? They're not just guessing. There's a very specific and pretty cool physical property they use as their target.
This is the magic number, negative 0.52 degrees Celsius. But what does it mean?
This is the secret key to everything. We all know pure water freezes at 0 degrees Celsius, but our blood and our tears aren't pure water. They have salts and other things dissolved in them. This lowers their freezing point to exactly negative 0.52 degrees Celsius. So, to make a solution perfectly safe for our body, scientists just have to engineer it to have the exact same freezing point. It's brilliant.
The process, which is called the cryoscopic method, sounds really fancy, but it's basically a logical four-step dance. First, they dissolve the drug in water. Then, they measure its freezing point. They see how far off it is from our target of negative 0.52 degrees Celsius. And finally, they calculate and add the precise amount of sodium chloride, just table salt, needed to lower the freezing point so it perfectly matches our body.
So the next time you see an IV bag, remember what's really going on. It's not just water. It's a marvel of bioengineering. It's a solution that has been meticulously balanced to match our body's internal environment, all to keep our cells from swelling up like hippos or shrinking down to nothing. It's all about respecting the fundamental rules of osmosis.
And that makes you wonder, doesn't it? We've just uncovered the invisible physics behind something as common as an IV drip. What other amazing, unseen principles of science are hard at work in the medicines and treatments that keep us healthy every single day?